Dear students, today we will learn about spherical polar coordinates. Just like we did in the case of cylindrical polar coordinates, here also we will compare every step with Cartesian coordinates so that learning will be easy. Consider a point P. First, we draw a perpendicular on to the xy plane. Let the foot of the perpendicular be Q, and we can see that it is in the xy plane. If we move a distance x along the x-axis and y distance along y-axis, we will reach the point Q. So, the coordinates of Q can be written as x, y. If we move a distance z, we will reach the point P from Q. So, we will get the coordinates of P as x, y, z. The infinitesimal displacement in the direction of x, dlx is equal to dx. Similarly, dly equal to dy and dlz equal to dz. In general, infinitesimal displacement in 3 dimension, dl vector is equal to dx x cap plus dy y cap plus dz z cap. Now we go to the spherical coordinate system. Let us locate the point P using spherical polar coordinates. We consider the same point P. The vectorial distance from the origin to the point P is the first spherical coordinate R. The angle drawn from the z-axis to the vector R in the clockwise direction is the second spherical coordinate or the polar angle theta. We already dropped a perpendicular from point P to xy plane and the foot of the perpendicular is point Q. It is on xy plane. That is, the vector OQ is the projection of vector R on xy plane. The angle drawn from x-axis to the projection OQ in the anti-clockwise direction is the last spherical coordinate, that is azimuthal angle phi. We already saw this in cylindrical coordinate system. It is the same phi. So, we have got the point P by using 3 coordinates r, theta and phi. The spherical polar coordinates of P is r, theta, phi. Now let us move on to directions. The vector drawn here in the direction of increasing r is r cap. This vector theta cap gives the increasing direction of theta, which will be 90 degree from r cap downwards. The vector phi cap direction can be found by curling the fingers of your right hand from r cap to theta cap direction. And we can see that it will be mutually perpendicular to r cap and theta cap. Now let us look at the range of r, theta and phi. We can see that r can increase from 0 to plus infinity. Theta we can see as we go from plus z-axis to minus z-axis increases from 0 to pi, that is 0 to 180, which corresponds to a half circle. Phi can be varied from 0 to 2 pi, that is one full circle from x-axis back to x-axis. Now consider the plane containing the z-axis, point P, point Q and origin. It is drawn here. The height along the z direction will be equal to the z coordinate of point P. OP is R and this angle ZOP from the figure is theta. From this we can see that in this right triangle, OQ or ZP is the opposite side to this angle and OZ is the adjacent side to this angle. So ZP or OQ will be equal to R sin theta and OZ will be equal to the Z coordinate, which is R cos theta. Now consider the plane containing O origin, x-axis, y-axis and point Q. This distance along the x-axis will be the x-coordinate and this distance along the y-axis will be the y-coordinate of point P. From this figure above, we can see that OQ is R sin theta. From this figure, we can see that the angle XOQ is phi. From this right triangle, we can see that XQ or OY, which is the y coordinate, is the opposite side and OX or x coordinate is the adjacent side. So XQ or OY will be equal to R sin theta sin phi and OX or x coordinate will be equal to R sin theta cos phi. So we have got all the three coordinates, z coordinate, x coordinate and y coordinate of P in terms of r, theta and phi. X equal to r sin theta cos phi, y equal to r sin theta sin phi and z equal to r cos theta. We have also seen that range of r is from 0 to infinity, theta is from 0 to pi and phi is from 0 to 2 pi. Now let us move on to infinitesimal displacement elements in spherical polar coordinates. The small displacement in the direction of r cap is dlr, which can be written as dr, just like dlx equal to dx or dly is equal to dy. Now consider theta cap direction. A small displacement in this direction is called dl theta. A vector moving in the direction of theta cap will have constant r. This r is seen to be moving in the theta cap direction. So r will not change. The only change is in theta. Phi also will not change. This small change in theta is denoted by d theta. So from the equation angle equal to arc by radius, angle d theta equal to arc dl theta by radius r, or dl theta equal to r d theta, which is the infinitesimal displacement in the direction of theta. Now consider phi cap direction. Infinitesimal displacement in phi cap direction is denoted by dl phi. Consider this vector r sin theta, which is moving a small distance in the direction phi. So there is no change in r or theta. The only change is in phi and this small change is denoted by d phi. Using the same equation angle equal to arc by radius, d phi is equal to dl phi by r sin theta, or dl phi is equal to r sin theta d phi, which is the infinitesimal displacement in the direction of phi. So we got the three infinitesimal displacements dlr, dl theta and dl phi, which is equal to dr, r d theta and r sin theta d phi. In general, dl vector, infinitesimal displacement vector in 3 dimension in spherical polar coordinates, can be written by dlr r cap plus dl theta theta cap plus dl phi phi cap, that is dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. Let us move on to infinitesimal area elements. In Cartesian coordinates, we have seen that area element in z direction will lie on xy plane. dAz can be got by multiplying the infinitesimal displacement elements in x direction and y direction, that is dx and dy, and the direction of this area element will be perpendicular to this area element, which is in z direction in this case. So dAz can be written as dx into dy z cap. Similarly, an area element in the y direction will lie on xz plane and can be written as dA y is equal to dx dz y cap. Similarly, area element whose direction is in the x-axis will lie on yz plane and can be written as dAx equal to dy dz x cap. Let's use the same logic to find out the infinitesimal area elements in spherical polar coordinates. Consider the small patch of area shown here in green color. Its enlarged picture is shown here. We can see that it lies on the surface of this sphere, so that r will be a constant for the patch because it is on the surface of the sphere. So what is changing? We know that theta is the angle from z axis downward in the clockwise direction and phi is the angle from x axis in the anti-clockwise direction. So along this line, which is shown here in purple color, phi changes, and along this line, which is shown in orange color, theta changes. So r is a constant for this whole patch while theta and phi changes. This area element can be found by multiplying dl theta and dl phi. Area of this patch will be equal to r d theta multiplied with r sin theta d phi. dAr equal to dl theta dl phi r cap, r d theta r sin theta d phi r cap, which is r square sin theta d theta d phi r cap. R cap is the direction of this patch which will be perpendicular to this patch. This is what we have already got. Now we have to find out the other two area elements dA theta and dA phi. Consider this figure. Consider this circular plate. Look at the blue patch area. Theta, which is the angle from z axis, will be constant for all the points on this plane. So for this patch also, theta will be a constant. In this patch, r will change along this line. From here to here, we can see that r, which is distance from the origin, keeps increasing. Phi, which is angle from x-axis, increases from this point to this point along the line. This is dl phi and this is dlr. This patch of area will have the direction perpendicular. So, which is the direction perpendicular to this patch? That will be theta cap. From z-axis to this patch, downward of this patch. That is theta cap. This area element can be written as dA theta and can be given by the equation dl phi into dlr, that is dr into r sin theta d phi, which is equal to r sin theta dr d phi in the direction theta cap. Now look at the blue patch of area on this circle. What is constant here? Phi. Phi, angle from x axis, is constant for this circle, every point on this circle. Along this line r will change and along this line theta will change. So this is dlr and this is dl theta. The direction of it will be perpendicular to this patch, that is phi cap. So this area element can be written as dA phi, which can be written as dr into dl theta, which is dr into r d theta phi cap. Moving on to infinitesimal volume element dV. In Cartesian coordinates, we saw that we get it by multiplying the infinitesimal displacement elements in all the three directions. That is, dV is equal to dx dy into dz. Volume element is a scalar and so there will be no direction. Now look at the spherical polar coordinates. Similar to Cartesian coordinates, we can get it by multiplying the three infinitesimal displacement elements dlr, dl theta and dl phi. Look at this figure. This is the infinitesimal volume shown in blue color. Along this line we can say that r changes. Along this line theta changes and along this line phi changes. So this is dlr, this is dl theta and this is dl phi. dr into r d theta into r sin theta d phi, which is given by r square sin theta dr d theta d phi, because we have followed the system of using small r for spherical polar coordinates. So replace all these capital R with small r. I hope you got a clear picture of spherical polar coordinates, and I hope you understood how using spherical polar coordinates will make our lives much easier when we deal with systems with spherical symmetry. Thank you.